Hi, welcome to this lesson on calculus optimization problems. Let's have a look at question 5. We're given a semicircle with a diameter of PQ and triangle PQR is inscribed in the semicircle. We want to find the perimeter of this triangle PQR such that the sum of the lengths of PR and QR is given as 10 units. Okay, so the goal here is to find the perimeter of triangle PQR. All right, so this perimeter can either be maximized or minimized depending on this context. But in order to find what those dimensions are and to find the perimeter, we're going to have to invoke some notions on Euclidean geometry here. So you can see how something like geometry now can be interpreted here within the field of calculus. So that's the beauty of mathematics. All the fields can speak to each other by some links that go towards them. Okay, so the first thing that I noticed that because PQ is a diameter, it'll have a central point here. We can call that point O if we want. And more so that the angle that is subtended here at the circumference is this angle here at the center is twice the angle at the circumference. So this angle here as a straight line is 180 degrees. So that's twice the angle here. So this is a 90 degree. That's super important because now we have a right angle triangle and we know some properties of right angle triangles, namely the Pythagorean theorem. We're also given that the length of PR, I'm going to call that y, and the length of QR, I'm going to call that x. Well, if I add those two together, x plus y, that must be 10 units. So that's important. We'll end up needing to use that somewhere. If we don't, then that's where we will get stuck. Okay. So first of all, this triangle is a right angle triangle. So let me extract it out here. Okay, so that's R, that's P, and that's Q. We see that's going to be X, that's going to be Y. But what is the distance here? Well, because we're given this as the diameter of the circle, that is broken up into the radius here and the radius here. Okay, so you could say 2R if you want, or you can just say little d for diameter, whichever one you want to write is fine. So to avoid any confusion, I'm going to put d there for diameter of the circle. Okay, so by Pythag now, so let's write there, by Pythag, the Pythagorean theorem tells us that x squared plus y squared must equal d squared. Okay, the diameter squared. All right, so how do I end up maximizing this perimeter? So first of all, we need a function for the perimeter depending on these dimensions. So first of all, the perimeter I'm going to call P is given by x plus y plus d. Okay, because the perimeter of this triangle is just the sum of the dimensions of the triangle. Okay, so we either want to minimize or maximize that. Okay, because they didn't tell us explicitly we are minimizing or maximizing, they just wanted a perimeter there. So depending on how we do this in calculus, it'll either be a minimum or maximum perimeter. I would wager on maximum because we want to create the largest possible triangle inside the semicircle, right? So we need the largest perimeter. Okay, so first of all, we need just one value. So far we have three variables. We have x, we have y, and we have the variable d for the diameter. Okay, so if I can just get everything in terms of one variable, okay, then I can maximize this perimeter. All right, so let's go ahead and check that out. Well, we know that x plus y is 10. Okay, so I can write y then as 10 minus x. Okay, so if I know that, then I can substitute it into here. So I'll have by Pythagoras x squared plus 10 minus x all squared, and that is the diameter squared. Okay, so the diameter squared is, so d squared equals x squared plus, okay, now if I square this term out, it's going to be 10 squared is 100. The product here is negative 10x, double it, so negative 20x, and then negative x squared is positive x squared. So I get 2x squared by grouping the like terms, minus 20x plus 100. So look at this now. I have d squared in terms of x values. Okay, so that's, I have d squared in terms of x values. So what have we actually got here? We know that we have x as a variable here, we know that y can be written as a variable in terms of x, 10 minus x. I'm going to say x equals x there. And then d, okay, so what I'm going to do is instead of d, I'm just going to write d squared. That's also written in terms of x, 2x squared minus 20x plus 100. Okay, so why is this important? Because all three variables x, y, and d are now written as a representation of just a singular variable x. Okay, so if I can maximize this perimeter, what I'm actually trying to maximize is the values of x, y, and d with respect to the just variable x. Okay, so I'm going to go ahead and rewrite this perimeter function out like this. Okay, so the perimeter is x plus y is 10 minus x plus, while d, we have d squared. Okay, so what happens is that now if we want to maximize d, so here comes the logical component we need to think about now. If we maximize d squared, that is also maximizing the value of d. So let's just think about that for a second. Let's say, for example, we found the max of d squared to be 100. Then the square root of 100 is 10. So that'll be 10. Because if we found values less than 100, let's say 64, then the square root of 64 is 8. Can you see 10 is greater than 8? Okay, so whenever you maximize d squared, you are also maximizing d as well. Okay, so what I want to do separately, okay, so we know that this is, I'm just going to write that as d for now. I want to maximize d squared. Then I'll find the maximum value of d. Okay, so far, the x minus x cancels and I'm left with 10 plus d. So that's my perimeter, 10 plus d. All right, and that makes sense. This length plus that length is 10, plus the diameter is 10. Plus the diameter gives you the perimeter value, 10 plus d. Okay, so we've reduced this problem down to maximizing the value of the diameter, d. But in order to maximize the value of the diameter, I'm going to maximize d squared first. And whatever that value is, I'm going to take the square root, and that'll give you the maximum value of d. Okay, so let's go ahead and make some space here. All right, so let's go ahead and try this. So now the function of d squared in terms of x is 2x squared minus 20x plus 100. So I want to maximize this. So to maximize this, what do? I'm going to find the derivative. So that's 4x minus 20 equals 0. Then 4x equals 20. I bring it across, divide both sides by 4, and I get x equals 5. So at x equals 5, d squared here is its maximum. Although when you look at this graph, because there's a positive here, the shape of it's going to be here. So it's actually a minimum. So we're actually minimizing this thing. Okay, so that's really interesting. We are minimizing it. Okay, so it turns out the problem is a minimization problem, not a maximization problem. So it's actually going to give us a minimum value here. Okay, so that's interesting. When you don't know whether it's minimum or maximum, you can actually interpret it from the end goal, the function that you identified from, and that'll tell you based on the shape whether it's a maximum or minimum. Okay, so at x equals 5, d squared is going to have a minimum value of what? 2 times 5 squared, that's 50. Minus 2 times 5, that's minus 100, plus 100. So d squared equals 50. That gives you the minimum. So therefore, d is going to be the square root of 50, which is 25 times 2. So that's going to give you 5 root 2. So therefore, the minimum perimeter, rather, when you minimize this question, the minimum perimeter is going to be 10 plus 5 root 2. And that is the perimeter value for this triangle. So again, let's just summarize what we've done here. From a given semicircle, we use Euclidean geometry properties. Angle at the center is twice the angle at circumference. That enabled us to get a right-angled triangle. From the right-angled triangle, we were then able to use the Pythagorean theorem, right, to get x and y in terms of d, right, or d in terms of x and y rather. And then the goal was to get a function of just one variable, and we decided x to be that variable here. So x, y, and d squared were all written in terms of x. Okay, then solving for the perimeter, x plus y plus d, we just get 10 plus d. So the goal to minimize this perimeter was to minimize d. But to minimize d, we had to minimize d squared. Okay, because the reason why I didn't minimize d directly is because then I would introduce a square root here, and then we'd have a problem when we try to do the derivative here. It will require more derivative laws than we've currently developed right now. Okay, you'd have to use something called the chain rule, right, which is another form of a derivative law. Okay, so what I did is simplify the problem. I minimized d squared first, and therefore that will give me a minimum as well for d. All right, so doing that, we got the x value to be 5. Substituting back for d squared, we got 50. And then to find d by itself, it became 5 root 2. Okay, so total, the perimeter that will minimize, the dimensions that will minimize the perimeter is given by 10 plus 5 root 2. That'll give you the minimum perimeter. And the dimensions are given as x, y, and r. Okay, so x here would just be, let's just come back here. X equals 5, that's what we solved. 10 minus 5, that'll be y as well. And then d squared here was 50. So d was 5 root 2. So this triangle here, to get the minimum perimeter, this triangle that we created, this right angle triangle, had 5, 5, and 5 root 2. So it's actually an isosceles right angle triangle that would minimize the perimeter here. All right, so really interesting question. Okay, I'll see you in the next one.